All righty, good morning, everyone. So let's do one more example. So just to remind ourselves that yesterday we talked about the potential of a continuous charge distribution. So we said that at some points P outside of continuous charge distribution, again, we just cut this guy up into an infinite number of pieces, sum them all together, which means we're going to do an integral. So the potential at that point is K integral dq over R, where again, this thing is simply a scalar, which means we don't care about directions. So we don't have to worry about cosines and sines and directions, vector proportions and blah, blah, blah. And of course, our dq is the same thing. So lambda dl for line symmetry, sigma dA for area symmetry, and then rho dv for our volume symmetry. So let's do one more example just to kind of finish this off, and then we'll move into the next chapter, which is where we would typically start for exam 3, but that's okay. Move on. So this one says that we have a line of charge, which has a length of L, where L is 12 centimeters, has a nonlinear charge distribution, which we're given in this case as lambda is equal to C times X, where C is just some constant number. So all that means is what? At this point here, there's zero charge. So my charge at this particular location is 0, and then my charge linearly increases till I get to this point here where I then have maximum amount of charge. Okay, so at this point, I'm going to have maximum amount of charge. And we're looking for the potential at this point of P relative to, again, spatial infinity. So as we talked about yesterday, since this comes from a point charge where the potential is 0 at infinity, so this will be the potential difference between this point and spatial infinity. Okay. So as always, we know that the potential at that point is simply K integral dq over R. So let's talk about dq again. So dq, as always, is some small little representative amount of charge. So I'm going to call this my dq. And let's define that as some distance of x from the origin here. Now, what type of symmetry does this guy have? Line symmetry, right? So we're going to rewrite this then as what? Lambda dl. But since I'm calling this the x-axis, and remember dl is simply the length of this little section here, how can I rewrite dl? dx, right? So finally, I'm going to write this as simply lambda dx. Right? So it's going to be my numerator. And then the denominator, in this case, of course, is r. So what's r? So r is this distance here. Right, so r again is the distance from the dq to the position of interest, which in this case is point P. Now I know d, I know x, so how can I rewrite r? So r is just equal to d plus x in this case. So let's put all of our pieces together. So this guy then is going to be equal to k integral lambda dx all over d plus x. And finally, what are my bounds of integration? Because I want to integrate only where the charge exists. So what are my bounds in this case? 0 to L, right? So I'm going to integrate this guy from 0 to L. Now, finally, we know that lambda, again, is simply C times X. So let's put that in. So I'm going to get finally a KC integral X dx over D plus X from 0 to L. Everybody's doing okay? Easiest way to solve this, of course, is the U sub. So let's use U sub. So U then is going to be D plus X, which means DU then is going to be a DX. Now on top, of course, I have an X, so I have to replace that X with U. So this tells me that X then is going to be equal to what? U minus D. Okay. My bounds of integration, of course, I'm going to solve U at first. X is equal to 0, which means U at that stage would just be equal to D. And then at X is equal to L, then U will be equal to D plus L. So this guy then is going to become XC integral from D to L plus D of then U minus D divided by U D. Everybody's doing okay? Now, of course, I can split this up into two integrals, which I'm going to do here. So this then is going to become the potential at points P will be equal to Kc times the integral from D to L plus D. So I'm going to break this then as what? U over U minus D over U. What was U over U? 1. Fantastic. So this guy's just going to be du minus d times the integral then from d to L plus d of then du over u. It's okay? Makes sense? What's the integral of du? U evaluated from d to L plus d. So what is that? Just L, right? So this guy is going to be essentially Kc times L minus d times, what's the integral of 1 over u du? Natural log. So I'm going to get the natural log of L plus d minus the natural log of d, but that's the same thing as natural log of L plus d over d. Mm-hmm. So I'm going to get a minus natural log of L plus d over d. Everybody's doing okay? You love doing calculus at 9 o'clock in the morning. Yeah, fantastic. Great. So from here, we're just going to plug in our numbers. So let's go ahead and do that, because in this case, it actually has numbers. Let's go ahead and do that. So we know this is 9 times 10 to the 9th. C is just a number which is given to us. So that is 28 pico. Anybody know what pico is? 10 to the minus something. Minus 12, right? So that's pico. Good. So it's 28.9 times 10 to the minus 12. Right? And then we're going to get L. So L was what? 12 centimeters? Is that right? Yeah, 12 centimeters. So it's going to be 0.12 minus D, where D is 3 centimeters. So I'm going to get a 0.03. Right? And we're going to get a natural log of, so this is going to give me a 0.15 divided by a 0.03. Is it okay? Keep plugging in numbers. What we find in this case then is my potential at this point is equal to 0.0186 volts. So this is my potential. Now again, even though we call it the potential at this point, again, it's the potential difference between this point and spatial infinity where my potential is 0. That's what this thing actually means. So it's not necessarily just the potential at that point. It's the potential difference between infinity and that point. Okay? We're officially done with this chapter. Everybody okay? Any questions? What's up, Kitty? Oh, wait. Never mind. Okay.
Whenever I saw that division, I was like, oh, how did you get L plus D over D? And I was like, oh, wait, you just did subtract.
Right. So I subtract those two with the natural logs, and that gives me the ratio. Exactly. So Louise asked a fantastic question this morning. Now that we're done with potential, are we ever done with potential? The answer is no. This will show up in the next 4 chapters that we're going to do. So let's not forget about potentials. Okay. So cool. So let's move on. So next thing we're going to talk about is, for the next chapter, what's a battery? What's the point of a battery? That's where we basically want to start. So first I'll talk about a battery is a special type of what's known as an EMF. So an EMF is what's known as an electromotive force. So even though it has force in the name, it is actually not a force. We'll talk about what this is. So what is first of all, an EMF? So an EMF is anything that supplies a constant, but then quotations, potential difference. So this is what we call an EMF. So an EMF is anything that supplies a constant potential difference. So basically what this means is if I had a battery, so let's say this is a battery, which again is a special type of EMF. So here's my battery. So a battery has a positive terminal and a negative terminal. Now, if I apply this thing to some sort of circuit, so I have some sort of circuit elements in this case, what happens is it forces positive charges from the positive side to move through the circuit and then come onto the negative side, so the positive charge ends up on the negative side. Okay. Now, in reality, this is not the way it works. We'll talk more about this later. It is actually negative charges which move in the opposite direction in reality. But by Benjamin Franklin, this is the convention that we use. Even in electrical engineering, this is the convention that you use, which is its positive charges moving away from the positive terminal into the negative terminal. But again, in reality, it's actually a negative charge moving from the negative terminal to the positive terminal. Now, what's the point of the battery? So the point of the battery is to bring this charge back to the positive place. Okay. So the point of the battery then is to carry this positive charge across the potential difference of the battery, which we're going to call as scribble E, which is the EMF, across the terminal of the battery. Right? Now, if I had a positive charge, does the positive charge want to move from the negative plate to the positive plate? No, right? It wants to move away from the positive plate as far as possible. So that means that we have to counteract the electric field, which is inside of the battery, which is pointing in this direction. It's going to be the direction of my electric field. So we have to overcome that Coulombic repulsion from the positive charge to the positive plate. This is what the battery does. So the battery supplies enough energy to move from this plate to this plate by doing work. Okay, so the battery supplies the work. So this guy supplies the work to move the charge from the negative plates to the positive plates. So this is the point of a battery. So the point of the battery is to do work onto the system by moving the charge from the negative plate to the positive plate, so that way it can still have the current, in this case, or the charges flowing through the system. Okay? What's up, Brandon? Is it negative? Yes. Correct. Correct. Because the battery has to do the work. So it has to do the work over the electric field. Absolutely. Yes. Absolutely. So cool. So in this case, what we define as the EMF, which we call this scribble E, again, this is what's called the EMF, is equal to the differential work per unit charge. So this is what we call the EMF. So the EMF is the work per unit charge to carry the charged particle from this side to this side against this potential difference. Okay. Now, what this means is this is what energy per unit charge. So this is the same thing as potential energy per unit charge, which means what's the energy per unit charge? What did we just finish talking about? Potential, right? So this thing is actually a potential. So this is a potential. So even though it has force in the name of it, it is actually not a force. It is a potential. This is what it actually is. So this is the EMF. So the EMF is anything that supplies a constant potential difference, where a battery is one specific type of EMF. You have other types of EMFs as well. You can have batteries, you can have AC circuits, you can have all kinds of different things. So alternating currents and blah, blah, blah. But we'll talk about those things when we get there. All of those are simply EMFs. So that's all I want to say about a battery. So next time we're going to talk about is what's known as a capacitor. So what's a capacitor? So we talked about this in lab, but what a capacitor is, it is a system of two conductors. So here's my conductors. So this is a metal and this is a metal, which are separated by some distance of d. So this is it. This is simply a capacitor. So what is the purpose of a capacitor? So the purpose of a capacitor is as follows. Let's say I take this capacitor and I connect it to a battery. So here's my, say, capacitor plates. And so these guys are, again, separated by a distance of g. And now let's say I connect these guys to a battery. So this has some sort of potential difference or some sort of EMF that this thing is applying. Okay. So what's going to happen? So we just said that the capacitor then wants to push positive charges from the positive terminal in this direction. Okay. So what's going to happen then is these positive charge then is going to get placed onto this plate. Simultaneously, that's going to kick out a positive charge from this plate, moving it back into the battery. Okay. Now this charge has no place to go because it can't jump across this gap because they can only move through wires. So this guy's going to be stationary there. Now what's going to do is it's going to take a second positive charge, push that onto the positive plate, kicking out another positive charge here, moving it in this direction. So overall, what's happening is this guy's becoming positively charged while this guy's becoming negatively charged. Okay. Now, as we talked about yesterday, to move the first charge onto here, since there was no initial potential across here, how much work did the battery have to do? Nothing, right? Now, move the second charge in there, did the battery have to do work? Yes, because now there's a positive charge here, so now I have to push this positive charge over top of the Coulombic repulsion to push this one onto here, right? So now the battery is going to take a third charge and try to push that one onto the plate. So that one then kicks off a positive charge in here, which goes on this side, which means they become more positively charged and more negatively charged. Now, how much work did that have to do to move the yellow one versus the work it had to do to move the orange one? It's going to have to do more, right? It has more of a Coulombic repulsion, which means it has to do more work. So what happens then is the purpose of a capacitor is to store energy from the work that the battery does to overcome this Coulombic repulsion. This is what the battery, or the purpose of the capacitor is. So the primary purpose of this guy is to store the energy done, or store the energy from the work done by the battery. Okay, so this is the primary purpose of the capacitor. It simply stores energy. It stores energy so we can get back that energy at a later time. So it stores energy for later usage. So it stores it for later usage. Now, this is the primary function of it. There are, of course, secondary functions. So some other secondary functions. Secondary function is this is actually the RAM in computers. So your RAM, which stores the binary code while you're actually doing calculations, is actually stored as charges or non-charges or energy versus non-energy of capacitors. So I have one capacitor here, another capacitor here, another capacitor here. Let's say this one has a charge on it, which means this one has charge, this one has no charge, this one has charge. This creates my binary system. So this would be a 1, 0, 1, for example. Okay. So your RAM is actually nothing more than a series of capacitors. That's it. So your computer reads this, creates a binary code. Another function is that this is actually surge protectors. So anybody have one of those power strips that has a surge protector in them? Nothing more than a surge or a series of capacitors. Okay. So in this case, what happens is the capacitors actually block the flow of currents because as it stores up, what will eventually happen is it'll create or go to some sort of a maximum amount of charge. So this become positively charged maximally. This will become negatively charged maximally, which means anything after that will not allow current to flow. Which means if your house was struck by lightning, the capacitors fill up, they will not allow a flow of charge, which means there's going to be no current, which means the power will not exceed the amount of what your computer, for example, can use, so your computer won't blow up. Right? This is the surge protector. So these are some secondary functions of a capacitor. But again, the primary purpose of a capacitor is to store energy from later usage by storing the energy from the work done by the battery to push the charges onto the capacitor to begin with. Okay with this? So what is the capacitor? So now we know the capacitor. So now, again, if I hook this guy up to a battery, so here's my battery. So what's going to happen then is that my capacitor then is going to reach some sort of, as we just said, maximum charge. So this guy's going to become positively maximally charged. This guy's going to become negatively maximally charged. And if we plot the potential difference versus the charge. So here if I plot the maximum charge versus the potential across the capacitor. So eventually this potential across the capacitor will equal the potential across the battery here. If I plot these two, what I find in this case then is there's a linear relationship between the two of them, where the slope of this linear relationship is what's known as the capacitance. So this tells me that C then times the potential is equal to the charge. So basically, if I increase the potential, I then increase the charge by what's known as the capacitance of the capacitor. So let's talk about capacitance. So capacitance then has units of, so my capacitance then is going to be equal to the charge per volt. So this thing is going to have units of coulombs per volt. And a coulomb per volt is what we're going to call a capital F, which is what's known as a farad. So the units of capacitance is what's known as the farad. Now, all this says then is we're going to determine the capacitance by measuring the charge and dividing that by the potential that is being supplied across the plates to then determine the capacitance of the capacitor. Now, this, depending on the geometry of the capacitor, is either really easy to do or impossible. Right? So for most practical situations, this thing is non-analytical, which means that we can't actually solve what it is because the geometry is just too difficult, which means you can't perform that integral, at least in closed form, to be able to actually calculate the capacitance. So in that case, the only way to determine the capacitance of the capacitor is basically to do this, apply different potentials across different capacitors, fit the straight line, and then determine the capacitance of the capacitor for most realistic situations, because the geometry is just too difficult. We can't actually perform that integral in closed form. So everybody knows that you can't perform every single integral on the planet. Right. So in the space of integrals, we can do that much. Now, if we know complex variables, we can increase it to that much because we can complexify everything and then do it in the complex plane and then bring it back to the real plane and find more. But for most of the integrals that we can ever write down, we cannot actually solve them. That was something I had to get used to when I actually went to the real life instead of math class, right? Okay with that. So what's that? How much do we approximate? Well, we have special functions for some things. So like hypergeometric functions, we have Bessel functions, all that different stuff. But again, those are kind of approximations. Those are series solutions. After that, we can't. We have to use computers and then basically numerically plot them. And then we can gain information about numerically plotting, mostly trends and things like that. But yeah, most things we have to use computer for is to actually numerically plot these things and stuff. So what's up? Yeah. Oh, how much of this here? Oh, good question. We can do approximations. So you can do, for example, depending on what the function is, you can do like Taylor series expansions. So in that case, you're expanding it about some sort of small parameter, and then you are approximating about that. Or we can do large limit things. So in that case, we can take things like, some R goes to infinity or something, and then do it out there. We can also do what are called interpolating functions. So if we had a complex, let's say, differential equation, then you can solve it near it, you can solve it away from it, and then you use an interpolating function that compares or merges the two together. We do series solutions, we do all kinds of different stuff. But again, all of those are varying degrees of approximations. So depends on what it is that you want and how well of a approximation that you want. So typically in a Taylor series expansion, for example, if you take the lowest order, that gives you the most dominant of what's actually happening in the system. And then everything on top of that would be a correction or a small modification of what it is that you're actually doing. So again, it depends on how far you want to go or to what level of accuracy that you want your solution to be. If you want to be as accurate as possible, you just do it numerically. It's the only way we can actually do it. So. Was okay? Now, if we have a good geometry, we can actually first solve the potential by doing the integral. And then from there, we can then determine the capacitance by knowing the charge, which is on here. Now, things to point out on capacitance is that number one, capacitance does not depend on the charge. Number two, capacitance does not depend on the potential. Even though it looks weird, because in the definition, it has both charge and potential in there, but it turns out to not actually depend on those things. And the last thing that's true is that capacitance only depends on geometry. So the only factor that actually comes into the capacitance is the geometry of the capacitance, which means that to change the capacitance of the capacitor, at least at this stage, the only way we can do that is by changing the geometry of the capacitor. The only way to change the capacitance. So basically all this implies then is what? The only way to change the capacitance is to change the geometry. Now I'm going to put that in a little bit of a star a little bit because this isn't 100% true. We can also add what's known as the dielectric, but we're going to talk about that at the end of this chapter. So let's look at how to actually calculate a capacitance if we have some sort of simple geometry. So let's look at a couple examples of this with simple geometries. So if we have a simple geometry, we can calculate directly. So no fancy shenanigans of Taylor series expansions and all that different stuff. We can actually do this. So let's do that. So let's do a couple examples of that guy there. So let's look at this guy. So this says, I'm going to do this one first. I'm going to do the other one first. Let's do this one first. Simple. So this wants me to find out what is the capacitance of a parallel plate capacitor. So here's my parallel plate capacitor. So I have two plates with equal areas. So here's my parallel plate capacitor. And these guys are going to be separated by some sort of distance d. This will be connected, say, to a battery. So this is going to have some potential difference across this. So it's going to be my potential difference, V. And let's say this is my positive plate, and this is my negative plate. Okay. Or from the side view, I simply have, what, two sheets here, separated by a distance of d. And these guys have a potential difference, V, across them. Or this is my negative plate, and this is my positive plate. Okay? So in this case, since this is negative, we can call this our zero potential, which means this plate then is going to be the potential of simply V. So what do we know? We know, going back to last chapter, that the potential difference across the plates is then equal to minus the integral from A to B of the electric field dotted by the differential line. Okay. So what do we know? We know, as we talked about before, that at least in the center portion of the plates here, the electric field is a constant. We know that the electric field is going to be perpendicular to the surface, which means for this one, the electric field will point this way. Let's call that E positive, and point this way, which is E positive. And for the bottom one, it's negative. So I'm going to have negative coming inward. So it's going to be E negative. And I'm also going to have E negative in this direction. Are you doing okay? Now, for funsies, let me extend this line in this direction. And let me extend this line in this direction. Basically, so we can kind of see what it is I'm talking about. So what do I know? I know the magnitude of E positive is equal to the magnitude of E negative, which is equal simply to the charge density divided by 2 epsilon naught. Okay? So again, for infinite sheets of charge, which this thing is approximately infinite sheet of charge in this area, then my electric field is simply this guy. Right? Now let's look at the total electric field on the outside. What's going to be true about the total electric field on the outside here? It's going to be 0, right? So out here, my total electric field has to be 0, which means on the outside of the plate, above it, my total electric field has to be 0. What about below? also 0. So this guy has 0 electric field on the outside. And what's going to be true about the inside? They're both going to be the same, right? So in this case, I have two functions of that. So my total electric field on the inside will simply be equal to sigma over epsilon. Okay. So it's going to be my total electric field on the inside of the plates because they both point in the same direction. Now I also know that my electric field is going to point this way, right? From the positive plate to the negative plate. It's doing okay. Now, what we want to do is integrate this guy by integrating from the negative plate to the positive plate because we want what? A positive potential difference, because this is going to be my final potential difference, which is the potential of the positive plate, minus the initial potential difference, which is that of the negative plates. But this guy here, I can simply call 0. So this is going to be then simply the potential difference across the plates. Okay? Now, what else do I know? I know my electric field points this way. VL, I'm going to take only in this direction, which means the dot product between the two of those, are they in the same direction or opposite direction? Opposite direction. So the dot product giving me a positive number or a negative number? Negative. So that negative is going to cancel this one. So this then is going to be equal to simply the integral from 0 to d of the electric field, which is sigma over epsilon naught, times the direction at which it is that I'm integrating. I'm going to call that the z direction. So let's say this is my z direction in this. Everybody's okay? Sigma over epsilon naught, of course, is a constant, so I can come outside the integral, and then I have the integral of dz. What's the integral of dz? Z evaluated from 0 to d, simply d. So this is going to be the same thing as sigma over epsilon naught times d. Okay? From there, I can now find the capacitance using this expression. So my capacitance then is going to be the charge divided by V, where V is the same thing as sigma divided by epsilon naught d. Now, I said it doesn't depend on the charge, and it doesn't, which we can see from here. Remember, this is the charge density, which is the charge per unit area. So this charge is actually going to cancel this charge. Right? Now, remember also that the charge density, again, is the charge per unit area, which means that this plate here has a total charge of capital Q. This is my area of A. I can then rewrite this then as Q over epsilon, or let's do it this way, Q d divided by epsilon naught times the area. Okay? So finally, my q's are going to cancel. Epsilon naught A will move to the top. So this thing finally says that for a parallel plate capacitor, this thing is going to be epsilon naught times the area divided by d. So this is for a parallel plate capacitor. This is something you definitely want to write down. We will come back to this a lot. Okay? So again, just to point out, does this thing here depend on charge? No. Does it depend on potential? No. It only depends on the area and the distance between the plates, which means it only depends on geometry. Which again means the only way to change the capacitance of the capacitor is either to change the area or to change the distance between the plates. That's it. So at a capacitor, I want to increase the capacitance of the capacitor. I can either increase the area or I can decrease the distance between the plates. If I want to decrease the capacitance, I either decrease the area or I increase the distance between the plates. Only two ways I could change the capacitance. Okay? And like I said, make sure you put stars next to this guy because we will come back to this a lot. So let's do one more example of this, another type of geometry that we can look at. And this is cylindrical. So this says we want to determine the capacitance of a cylindrical capacitor that exists of a wire or an inside cylinder of radius A surrounded by a coaxial cylindrical shell of radius B, and they both have some sort of length L to them. So let's draw our picture. So here I have an inside cylinder or wire where this guy has some radius of A. And then I have a coaxial shell around this guy. So here's my coaxial shell. which has some radius of b, and each one of these are of equal length, which we're just going to call L. So what it wants me to do now, again, is determine the capacitance of this capacitor. Okay. So just for funsies, I'm going to say the inside one has the negative charge, and the outside one has the positive charge. Okay. Which again means I can arbitrarily call the inside one my potential equal to 0, and then I can call the outside one my potential V. We doing okay? Now, in this case, what's going to be the direction of the electric field? Inward, right? So in this case, this guy's going to have an electric field pointing inward. So it's going to be a direction of my electric field from the positive plate to the negative plate. And same thing out here, my electric field will be 0. Out here, my electric field will be 0. So the only place the electric field is going to exist will be inside of that area between the two cylinders. Everybody's doing okay? So again, to determine the potential difference, we're going to say our potential then is equal to the potential difference between the two plates, which is then equal to the integral from A to B with a negative sign of the electric field dotted by DL. He's doing okay? Now, another thing I know is for a infinite line charge, so basically meaning that somewhere in this region here, I can pretend that this is an infinite line charge. This is where the greatest amount of contribution is going to come from. Now we know is from the last exam, Gauss's law told us that for an infinite line charge, the electric field is lambda divided by 2 pi epsilon naught times r. Okay, where r is the distance from the center of this guy outwards, right? So this is my distance of r. We're doing okay? Gauss's law is coming back to haunt us. That will also be a thing for a long time. Always okay? Cool. So in this case, then, we're going to plug that in here. So in this case, our DL then, we're going to go, again, it's going to be from the negative plate to the positive plate, which means we're going to integrate. If I find a different colored chalk, there we go, in this direction. So my DL is simply going to point this way. So in this case, our DL then is going to be the same thing as dr in the r hat direction. Okay. Now again, since my electric field points inward, my DL points outward. What's the dot product between the two of those? Is that going to be positive or negative? Negative, so it's going to cancel this negative sign here. So this is then going to be equal to the integral from A to B, where A is the radius of the inside, B is the radius of the outside, of then lambda divided by 2 pi epsilon naught r dr. Everybody's doing okay? Lambda over 2 pi epsilon naught, of course, is the constant. I can pull that now. What's the integral of 1 over RdR, or pirate speak? Natural log. So I'm going to get the natural log from A to B, which is the same thing as the natural log of B divided by n. Okay? So finally, we get that the potential is going to be the same thing then as what? Lambda divided by 2 pi epsilon naught natural log of B over n. This is my potential. Now, from here, we can finally now find the capacitance. So the capacitance then is the charge per potential. So it's going to be the same thing then as what? 2 pi epsilon naught charge divided by lambda natural log of B over n. Okay? But we also know charge is the line charge, which means that, let's do it this way, my charge density is the same thing as the charge per unit length. So I can replace that here. So let's do that. So it's going to be the same thing as Q over L. So this Q is going to cancel this Q. The L moves to the top. So finally, we have our capacitance then is going to be 2 pi epsilon naught L divided then by the natural log of V over. Oh, we're doing okay? So this then is my capacitance of a coaxial cylinder. That one you don't have to memorize. We probably won't come back to that much. That's just an example. Is it doing okay? So again, for simple geometries, we can determine the capacitance by simply taking the potential, which we can find by doing the beautiful integral here, as long as we know the electric field. If we don't know the electric field, then we can use the other one, which is the K integral of VQ over R. Find it that way. And then from there, we take that charge divided by that potential, and then we're done. Again, for simple geometries. If I don't have a simple geometry, I cannot do this because I cannot determine this integral here. So in that case, I just have to plot them by doing experimental measurements. That's it. Okay, so let's a capacitor. So what are we going to do with capacitors? Well, we're going to put capacitors into circuits because, again, the primary purpose of a capacitor is to store energy for later usage. So we basically just want to put these guys into circuits so we can have them store energy. So let's talk about how this works. So there are two different ways that we can put capacitors into circuits. And the first way is what's known as series, and the second way is what's known as parallel. So let's talk about this. So what is series? So series is we're going to connect it to some battery, and then we're going to have a capacitor here. Let's say a capacitor here, and then some sort of capacitor here. So this is what's called series. So series means that these guys are connected in a line where the charge, which is coming from here, has no place to go other than through all of these different capacitors. What we call series. Okay. Parallel is I would have a battery here. And then again, let's say I have 3 capacitors. So these guys are connected in what's called parallel. So this is called parallel because the charge which comes out of here will come up through here, move into this position, but then it has a choice. It can either go through this line, it can go through this line, or it can go through this line, which means that some of the charge will go this way, some of the charge will go this way, and some of the charge will go this way. So parallel is defined by these guys here, which we call nodes, where nodes means it has a choice. So the charge which is coming through has a choice to go 3 different directions in this case. Right? So let's say this is C1, this is C2, this is C3, this is C1, this is C2, this is C3, and this is my potential, and this is my potential. Now, typically we have to arrange these guys like this because of manufacturing limitations. What does that mean? That means that is it economical for me to create every possible different capacitance that everybody would ever need in their lives? No, of course not, because how many different capacitors would I have to make? A lot or infinite, right? Because one person may need, I don't know, 1.1 farad worth of capacitor. Another one might need 1.2. Another one might need 1.11, which means you have an infinite number of capacitors that you would have to make. Now, based off of the number of materials that we have, that's not as well as how much money it would cost to make these things. So first of all, let's say if I have a certain amount of material, could I make an infinite number of capacitors? No, even if I could, how many of each capacitor could I make? Maybe 1, right? Which means if 2 people need the same capacitance, well, you're screwed, right? Because somebody else already bought it. Does that kind of make sense? So in this case, what that means then is for manufacturing purposes, it's a lot easier just to make certain types of capacitors. So if I need a certain capacitance, what we usually do are then going to be put capacitors into parallel or capacitors into series to create the capacitance of what it is that I want. Which means that this circuit here and this circuit here are equivalent to 1 battery connected to 1 capacitor, which is what we call the equivalent capacitance. All right. So our claim then is that these 3 connected in series act as if it's 1 capacitor of some equivalent capacitance. These three, which are connected in parallel, all act together as if they are one equivalent capacitance. So the next thing we want to know is what is the equivalent capacitance when we connect them in series, and what is the equivalent capacitance when we connect them in parallel? So let's talk about this. So let's find our equivalent capacitance in series. Let's do that one first. Now, what do we know? So in general, this is going to have a different capacitance than this, which is going to have a different capacitance than this, which means what? The amount of charge which comes out of the battery, let's call that Q, this charge will not be the same as this charge here, and this charge here, and this charge here. Okay? This means that when the charge comes on here, this is going to have amount of charge of Q1. This guy then is going to have amount of charge of, say, Q2. And this one then is going to have amount of charge of, say, Q3. Each one of these then is going to have a potential difference of V1. This is going to have a potential difference of V2. And this is going to have a potential difference of V3. Now, let's go back to the statement I just said. Can this one have the same charge as this one? Can have the same charge as this one? Have the same charge as this one? Let's think about that. Now, if all of this is connected in one line, what does charge conservation say? Sum of all three would be the same, but again, since this is pushing it all in the same line, that means whatever positive charges come off onto this one would have to push the same number of positive charges off of here, so this would become negatively charged. Where can those positive charges go? Only to this one, right? Which means this one is going to have the same number of positive charges as this one kicked off, which is going to kick off the same number of positive charges from here onto here, which is then going to kick off the same number of positive charges onto here. So by charge conservation, what that means then is that each one of these is actually going to have identically the same charge. This kind of makes sense? Now over here, that will be different. All of these will have different charges because the charge that comes in here will have a choice to go in this direction, or this direction, which means a fraction of the charge of this guy will go here, a fraction will go here, and a fraction will go here. But in this case, because they're all connected in a single line, the charge this guy forces onto this plate has to be the same as this plate, which has to be the same as this plate because they're all connected in a single series. Okay? So what does this tell us? This tells us that in series, all the charges must be the same. Okay? So that means in reality for this guy, Q1 must be equal to Q2, which must be equal to Q3. Now, if they all have different capacitances, though, and they all have the same charges, what has to be true about the potential difference across each one? Those have to be different, right? So it has to be true is that here, this potential has to, in general, be different than this potential, which has to be, in general, different to this potential. But what has to be true about the sum of the three of these compared to this one? Right, or this is what you said earlier. They have to sum to that guy, right? So for series, what has to be true is that the potential drop across each one of these capacitors must sum to be equal to the potential gained by the battery. Okay? Now go a little bit further from here. What we know is that Q is equal to C times V, which means V then is equal to Q over C. So that means this side is going to be equal then to Q over C1 plus Q over C2 plus Q over C3. Now, since this picture here has to be the same as this picture here, meaning that the charge that comes out here has to be the same as the charge here, then our assumption is that this charge for CEQ has to be equal to the sum of those three. Because this picture here is identically the same as this picture. Is okay with this? So finally, we can cancel out then the Q's. So what this finally tells us then is that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, or in general, 1 over the equivalent capacitance is equal to the inverse sum of all the capacitances. Okay, so this says then that's what? If I have capacitors in series, I add them together inversely. I take 1 over each one of them, add them all together, and then to find the equivalent capacitance, I invert that. Okay, what does this have to the overall effect of the capacitance? Does it increase the capacitance or decrease the capacitance? Going to increase it or decrease it? It's decreasing, absolutely. So this decreases the overall capacitance. So if I ever want a capacitance less than the capacitance that I have of my capacitor, I have to add them in series because that's going to overall decrease the capacitance. Now, the way you can kind of think about this physically is that by stacking all these capacitors on top of each other, you are effectively increasing the distance. And as we saw with the parallel plate capacitor, this was epsilon naught over d, which means as I increase the distance, I'm decreasing the capacitance. So this is physically what this actually means. So cool. We'll pick up with this tomorrow. We'll start capacitors in parallel, and then we'll start doing some examples of this stuff. All right, go Danya. Have a good day. Stop sweating.